Hi
Okay.
everyone.
Yeah. So welcome everyone. So today is my pleasure to welcome Boya Hou, who will be talking about nonparametric sparse learning of dynamical systems. Yeah. Thank you, Boya.
Thanks for the invitation. Um, so I'm going to talk about my work on nonparametric sparse learning of dynamical systems. OpenAI released the ChatGPT 4 a few days ago, and it has been almost more than a year since the release of ChatGPT. Every a few weeks, there are new headlines saying we are one step closer to the wave of autonomy, but we all know that we are still at the very beginning of the wave of autonomy. If we look at the bright side, we have witnessed impressive performance in applications such as dexterous manipulation of Rubik cubes and playing the game of Go, chess, and Atari. I would like to bring your attention to the fact that the method that enable those successful applications combines deep learning with reinforcement learning, and they do not require a physical model derived from first principle modeling. But when we take a closer look at those successful applications, they're actually impressive demos, but are still far away from the promise of autonomy, such as autonomous vehicles and humanoid robots that looks and acts like human. On the other hand, if we fast backwards to the 1960s, we are already being able to send humans to space even without deep learning or reinforcement learning. In fact, the system and control theory has been very successful as long as we have a reasonably well understood dynamical systems. And this motivates me to think why model-based approach is losing its allure. So we try to bycome the trouble to coming up with a model if first principle models are not always conceivable or models are too complex to be useful. For example, if we have a really complicated power grid with lots of distributed energy resource, even if we can have an accurate model, it will be hard to design a control mechanism to accurately control those complex models. Another important reason is that the environment itself may evolve over time. For example, when we think about the case of disease prevalence or traffic control, the underlying dynamical system itself are evolving, and we need to coming up with a model that could adapt to the changing environment. This motivates me to think, what is the role of a model in autonomy? In my opinion, a model is a representation of an agent's existing knowledge, and the experience encoded in the model allows for knowledge to be transferred to related environment and even extrapolated to unknown environment. For example, Newton's second law is useful across various scenarios from designing a spacecraft to kick a football. And it is useful in the sense that it provides a starting point for our task, and it is useful even without perfect measurement of mass or force. If we're thinking about how humans make decisions, we actually adopt a model-based decision-making and model-free decision-making strategy in parallel. For example, I learned how to drive on perfect road condition, but as I moved to Illinois, I need to handle lots of unexpected weather conditions such as snow. And in this case, the model-based part is my previous driving skills, and then I still try to learn how to deal with icy condition on the fly, and this is the model-free part. A pure model-based method is also useful. For example, because models are interpretable and is more structured, it also have more provable guarantees. But on the other hand, a pure data-driven method learns a control policy directly from data, and it requires less domain knowledge. In my research, I tried to learn a sparse model to represent the existing knowledge, but in the hope that we could also allow for data-driven tuning to perfect control designs. Then the first question is how to represent a dynamical system. Let's consider a Markov dynamical system described by the transition kernel P. One can then associate a Koopman operator that acts on the observables of state space. So in short, the Koopman operator governs the evolution of functions, and K acting on F assigns the value of F one step forward in the future. So instead of looking at how the state space evolves in time, the Koopman operator gives the finite state space into an infinite dimensional space of functions where the Koopman operator governs the evolution of those functions. Then the next question is, given a data set, how could we learn a Koopman operator such that the error is bounded with high probability? A most common technique is probably one start with a set of basis functions, and then we then try to learn a finite dimensional approximation of the Koopman operator over the finite dimensional subspace. But as one could imagine, we want those set of subspace to be rich enough to represent the system dynamics. For example, we would want the subspace to be an invariant subspace of the Koopman operator. But it can be hard to choose a pre-selected set of functions that are rich enough, and the member of those functions would grow with the high dimension of state space. And one method to circumvent this curse of dimensionality issue is, instead of choose a set of basis functions, we resort to the kernel trick. If you have learned about support vector regression in any machine learning class, then you must have heard of the kernel trick. So a simple example is, suppose we have a classification task in a two-dimensional state space. So let's say I want to separate the red from the blue, but there is no simple decision boundaries in the two-dimensional state space. So instead, I give the point to a higher dimensional state space where we can find a supporting hyperplane to separate the blue from the red. So a way to understand the kernel method is, instead of solving problems in a low-dimensional state space, we give the problem into a higher dimensional space where the problem becomes easier. So now we are ready to formally define a reproducing kernel Hilbert space. Let's consider a positive semi-definite kernel functions. Then a reproducing kernel Hilbert space is defined as the span of kernel function centered at every data point. A defining feature of the reproducing kernel Hilbert space is the reproducing property, which says the evaluation of every point can reduces to an inner product between the function and the kernel function centered at that data point. We can also define a feature map phi at x as the kernel function centered at x. And through my presentation, I will assume the kernel function is bounded and measurable. Now we have defined the Koopman operator. When interacting with the RKHS, let's first recall we have defined a feature map phi as the kernel function centered at x. One can then define a cross-covariance operator as a generalization of the covariance matrix to an infinite dimensional space, and then one can define. It has been defined that the kernel Koopman operator can be defined using the composition of a pseudo-inverse of a covariance operator with a cross-covariance operator. Now, to circumvent the invertibility issues, one often uses a regularized version of the kernel Koopman operator. Now, given a set of data sets, we can first reorganize the data set into snapshot pairs, and then the next goal is to learn the kernel Koopman operator from data. The most straightforward way to compute an empirical estimate of the kernel Koopman operator is to first compute an empirical estimate of the covariance operator using sample average. Then one can compute a regularized empirical estimate of the kernel Koopman operator by composing the empirical estimate of the covariance. But as we can see from these two expressions, the model complexity of this empirical estimate is captured by the causality of the data set, which is capital M. And as one could imagine, as the number of data sets grow large, they will create computation and storage issue. In fact, this curve of kernelization is not new for learning in RKHS. And let's first take a digression to, instead of thinking about learning an operator in RKHS, let's take a digression to think about the learning of a real-valued function in RKHS. And here I will introduce the notion of compression and how to construct a sparse estimate in RKHS. So let's recall the RKHS is defined as the span of kernel functions centered at every data point. Now, as we have M samples, we can construct a subspace which is defined as the span of kernel function centered at every point in the dataset. By the well-established representative theorem, we know that if we want to solve regularized least-square problems in the RKHS, the optimal function can be written as a linear combination of kernel functions centered at every point in the dataset. So now let's suppose the regression function is plotted in the red line. And as the number of samples in the dataset grow large, this expression also suggests that the learning with kernel will create computation and storage issues. Now, one way to get rid of this issue is to prune the dataset to construct a compressed dictionary where we only use a subset of the actual dictionary. Then if we just randomly throw away data set, then we might end up with a bad estimate as shown in the blue line. So the punchline here is we only throw away data set if there is no information added to the true estimate. And one way to construct such a compressed dictionary is by using the coherence condition given in the bottom line here. So we start by choosing a sparsification parameter gamma, which lies between 0 and 1, and the left-hand side of the equation can be understood as the cosine angle of the kernel function centered at every data point. So essentially, the left-hand side tells us how much the data point looks alike with respect to the kernel function. And if this cosine angle, if these 2 points are orthogonal, then the quantity on the left-hand side is 0. And on the other hand, if the two kernel functions centered at the 2 points are aligned, then the quantity on the left-hand side becomes 1. So one could imagine as we reduce the value of gamma, we would obtain a less coherent dictionary with fewer elements in the sparse dictionary. So this is how to construct a sparse dictionary for learning a real-valued function in RKHS. Now let's go back to how to learn a compressed estimate or sparse estimate of the kernel Koopman operator in RKHS. So recall the regularized version of the kernel Koopman operator is defined as the composition of the covariance with the cross covariance, which is a Hilbert-Smith operator on H. Now, suppose we are given a data set that consists of the snapshot pairs where x plus is one-step propagation of x through the system dynamics. And when because the kernel Koopman operator is a Hilbert-Smith operator, it is also known that the space of Hilbert-Smith operator is isomorphic to the tensor product space. So the way we construct a sparse dictionary for learning the operator is by first define a kernel function on the product space. One can then design a coherence condition that is given by this line, which is very similar to the one that we have for learning a real-valued function. And the only difference is instead of using a kernel function that defines on the state space X, now we are considering a kernel function that defined on this product space. Using this modified covariance condition, one can then construct a compressed dictionary based on which we can compute an efficient estimate of the empirical covariance and cross covariance operator based on the compressed dictionary. And then we can construct a sparse kernel Koopman operator by composing the sparse estimate of these two covariance operator. So here I will first show an example of what happens if we use a sparse estimate of the kernel Koopman operator. Let's consider a toy example of a Duffin oscillator where the system dynamics exhibit two stable equilibrium points and it have two regions of attraction. So as we all know that the Koopman operator is a linear operator, and we can compute its eigenfunctions and eigenvector. In particular, the eigenfunction can reveal global stability property of the underlying dynamical systems. I will introduce that in details later, but now I just wanted to show you some results of what happens with the sparse learning method. So suppose we can see from this bottom figure that the first three figure, the leading eigenfunction can accurately reveal the two regions of attraction, but the last one fails to do so. This is because as we are throwing away more data, we are losing useful information about the underlying dynamical systems. And this motivates us to perform a theoretical analysis of our method. So let's suppose we have IID samples, then we have a high probability bound on the operator norm of the sparse estimate of the kernel Koopman operator. What this term on the right-hand side tells us is the empirical estimate depends not only on the number of samples, but also on the sparse parameter, the gamma. So we recall from the last slide, we see that as we have a smaller gamma, we have a less coherent dictionary with fewer arguments in the sparse dictionary. So the second term on the right-hand side actually captured the price we pay for sparsification. More importantly, we have shown that if the state space is compact and we have a continuous kernel, the sparse dictionary actually saturate at some point, which means even if we have an infinite number of samples, that is the value of m grows to infinity, the cardinality of the sparse dictionary remains finite, and so the second term will goes to 1. the second term inside the bracket will goes to 1, and we are left with a term that is square root of 1 minus gamma squared that captures the price we pay for sparsification, and this term will not go away even if we have an infinite number of snapshot pairs. So this is the result for sampling for learning with IID samples. But since we are interested in learning at dynamical systems, and it makes more sense to say we are sampling from trajectories. And our result can also be applied to learning from trajectories where the underlying process is fast mixing. So in this case, we assume that the mixing coefficient is known to us, and instead of using all the samples, we create a subsample of all the datas which are separated by S steps apart, and the effective numbers becomes M over S instead of all samples. Notice that on the last term here, we use a fixed regularization term. This result can also be applied when we consider a decaying regularization term. So this is the first result of, yes.
Yeah, sorry, I just wanted to ask you a question. So here the kappa is it like a function that you choose yourself? I don't understand the
gamma,
kappa. No, the kappa continuous in the first bullet point.
The kernel is continuous.
So you choose the kernel.
Yes.
Okay, and then the final operator that you want, or the final kernel that you want to get, is a linear combination of kappa centered at the data points, right? Just to make sure I understood correctly.
Yes.
So the k that you want to learn is AI multiplied by kappa xi something, right?
No, so
you're
I
just
first
learning
choose a kernel
terms.
function, and then the kernel function will define a feature map. So the feature map is the kernel function centered at data point, and then then one can define a covariance operator, which is basically the expectation of the tensor product of the feature map. So then,
so the kappa is a choice, right? So phi x
yes,
equal to, so kappa is a choice, and then you have one formula where you have the sum of f is equal to the sum of AI kappa
that
xi.
is
So
for
what is that?
the learning real valued function. So I use this slide to explain why we need sparse learning instead of. So I'm trying to make the point that instead of using all the samples, we can construct a sparse estimate, which we only use part of the sample in the whole dictionary. So is this the equation you are looking at?
Okay, yes. So I don't want to take too much of your time. I just have two small questions. So how do you choose the kappa? And the second question is, what are you learning exactly? So what are the numbers or coefficients or matrices you are learning?
It's probably easier to start with the second. So I'm trying to learn the operator K, which is the
Through?
composition of the covariance. So these covariance have empirical estimate, which are the sample average of this feature tensor product of feature map. And once you have this, you can construct an estimate of K.
So it seems to me that once you have the phi, there's nothing to do, right? If you have, because you have a formula.
Yes. So in the first part, you have a formula there, and then so I'm trying to learn a sparse estimate. So instead of using all the samples, I'm trying to learn a sparse estimate of the empirical estimate. And then as I show here, you can't just randomly throwing away data point away. Otherwise, you should have a mechanism to decide how you construct a sparse dictionary. And the mechanism I'm using is actually not the only way to construct sparse dictionary. There are other methods such as random Fourier feature or Nystrom method. But this is what I'm using. And then once I have a dictionary, then I can construct the operator. And then the next question is, what are the theoretical guarantees of this sparse estimate of this operator?
Yeah, that I understood. So the kappa, how do you choose it?
That's a very good question. So
Okay,
it
let's go
just
answer that.
depends
Thank
on
you.
dynamical system, and it's really it's difficult to choose. I think there are some recent papers on how to use a deep neural network to choose a kernel function for different dynamical systems. I can point you to the paper after this talk, maybe.
Thank you for taking the time.
But we also have our own techniques that we developed with Hou and Ohadi on learning the kernels from data. So yeah, I can also refer you to that as well. Yeah. So with the using kernel flows and sparse kernel flows. Yeah. So we don't have we don't need neural networks to learn kernels. Yeah.
Why I asked the first question about what are you learning, because I know that if you have an over-parameterized neural network and you're trying to learn some parameters, there are some works that say that you will always go towards a sparse solution. So a lot of the coefficients will be almost zero. So that's why I wanted to see what you learn by learning.
Okay. So this is actually the first part of my talk. A brief recap is we defined we have seen the definition of the kernel Koopman operator, which encode a nonlinear dynamical systems, and I have introduced nonparametric sparse learning of the kernel Koopman operator. I will then talking about how to learn a continuous time Markovian dynamics in RKHS. So let's suppose there are some continuity in the stochastic. So let's suppose we are interested in a diffusion process and where we can associate an infinitesimal generator that described the movement of the process over infinitesimal time interval. As we can see from this general definition of this generator, it actually acts like a differential operator. And so the first question to ask is, what is the domain of this generator of the Koopman operator? So our result established that when the kernel function is bounded continuous and when the system dynamics is invariant under the Koopman operator, then the domain of the generator is the whole RKHS. So this is a very strong result, and it has not been established before. And one of the reasons that we can say the domain of a generator is the whole RKHS is because of this invariant assumption, where we assume that the RKHS is an invariant subspace under the system dynamics. And then the second question is, as we shall see from the expression, it involves taking a partial derivative of the kernel function. So the result we have established here is a generalization of the partial derivative reproducing property. So it said that when taking a partial derivative of the kernel function, it also belongs to the same element. It also belongs to the same RKHS, and the partial derivative of a function f evaluated at x have something similar to the reproducing property, that is, this partial derivative reduces to the inner product of a function and the partial derivative of kernel function. So this result has been established when the state space is continuous. But since we are interested in a diffusion process, when the state space is compact, the compactness of the state space sometimes is too stringent. So we relaxed that assumption that the state space is compact, but instead we are considering a kernel function that it is continuous differentiable and vanished at infinity. So after these two properties that we have established, then we can define something called a partial derivative a covariance type operator, where we can define the embedded generator as the composition between a covariance, the inverse of a covariance, with the covariance type operator. And the reason that we are going through all these two definitions to arrive at this formula is because it looks similar to the discrete time case. So based on this formula, it's very easy for us to apply the framework that we derived for the discrete time case and apply it to the continuous time case. So as we can see here, the theoretical guarantee is also very similar to the discrete time case. And I would emphasize again here is that so the sample complexity depends not only on the number of samples, but also on the specification parameter gamma. And as we decrease the value of gamma, we obtain a less coherent dictionary with fewer arguments. And the result, so this result, we assume that the drift and the coefficient are known, but in our paper, we assume we also have an algorithm where these two coefficients are not known, but instead it is estimated from data. So we have seen that how to learn a discrete time and continuous time dynamical system through the Kuhlmann operator. I will then introduce two applications of using the kernel Kuhlmann operator to analyze unknown nonlinear dynamical systems. So in the first, we consider a four-well dynamical systems where there are four metastable sets, and the trajectory will stay in one of the four metastable sets for a long time before real transition happens as jump between the four metastable sets. On the right panel, we have seen that we are able to characterize the four metastable set based on the estimated kernel Kuhlmann operator. And the procedure here is we first construct a sparse estimate of the kernel Kuhlmann operator from data. Then we can learn the eigenfunction, the leading eigenfunction of the learned sparse estimate, sparse estimation of the operator, where the leading eigenfunction reviews four metastable set. And the takeaway from this simple example is that the leading eigenfunction of the kernel Kuhlmann operator encodes global stability of an unknown dynamical system. In the next example, I will use this property to analyze complex power system dynamics. So in the power systems, there are usually three states of the systems. Under normal operating conditions, the power system operates at an equilibrium point. Then a fault might happen. This could be due to a lightning strike line or generator malfunction, where a fault happens, which moves the system away from its equilibrium point. Then we clear the fault, and hopefully after the fault is cleared, the system will return to a new equilibrium point. Then the question for the transient stability analysis of power system is what is the maximum amount of duration that a fault can last before the system lose its stability. So in order, perhaps the most widely used method is the time domain simulation, where one starts with various starting points of the post-fault dynamics and try to see when the system will diverge from its equilibrium point. But the time domain simulation requires a physical, detailed model derived from first principle modeling, which might not always be available. In particular, and this is not available when we have renewable energies that introduce lots of uncertainty, or black box inverters that prevents us to get a detailed model of the power system dynamics. So here I will apply our sparse learning algorithm to perform a transient stability analysis of the power system. As we have seen from our previous example, we can use the leading eigenfunction of the learned Koopman operator to characterize the region of attraction of the dynamical systems. So here, let's suppose we have already constructed our region of attraction shown in the gray area, which is the region of attraction of the post-fault dynamics. Then, starting from an off-on trajectory x0, two scenarios can happen. If we clear the fault before the fault on trajectory leaves the region of attraction, then the trajectory will converge to a stable equilibrium point. But on the other hand, if we clear the fault after it leaves the region of attraction, then the system dynamics will diverge. So in order to answer whether the system will converge to a stable equilibrium point or diverge, we wanted to know what is the maximum amount of duration a fault can last before the fault on trajectory leaves the region of attraction. On the left-hand side, we have plotted the eigenfunction evaluated at the fault on trajectory. So as we can see, the leading eigenfunction take on constant value both inside the region of attraction and outside the region of attraction, but it takes on two different values. As we can see here, when the trajectory is inside the region of attraction, the leading eigenfunction takes on the value of 1, but when it goes outside the region of attraction, the leading eigenfunction drops to 0. So in our algorithm, the jump when such transition happens is our estimate of the critical clearing time. And as we can see from the panel, we apply our algorithm to an IEEE 39 bus systems, and the empirical estimate of the critical clearing time could accurately match those results obtained from the time domain simulation. In my second example, I will apply the sparse learning algorithm to propagate uncertainty in initial condition through unknown nonlinear system dynamics. And in order to introduce our mechanism, I will first introduce a concept called Hilbert space embedding of probability distribution. So let's first consider we have a random variable x. Then the kernel function centered at x is a random element in the reproducing kernel Hilbert space, and the kernel mean embedding is defined as its expectation. And also for uncertainty propagation, instead of using the Koopman operator, we are interested in using the adjoint of the kernel Koopman operator, which is also related to the conditional mean embedding operator in the statistical learning literature. So here, for the uncertainty propagation of a dynamical systems, we recall that a dynamical systems described how states evolves over time. And when the initial point of the system is uncertain, one can represent this uncertainty through a probability distribution. Here, instead of looking at how the probability distribution is being propagated forward in time, we first embed the initial uncertainty into the RKHS through the kernel mean embedding introduced in the previous slide. One can then show that the adjoint of the kernel Koopman operator can propagate those embedded distribution forward in time. So in essence, the adjoint of the kernel Kuban operator U acting on the kernel mean embedding will give us the embedding of probability distribution one step forward in time. That is the embedding of probability distribution at time t equals 1. So one can then obtain the embedded uncertainty at time t by letting the operator U acting on the initial embedded uncertainty t times. So here is also a simple example of applying our uncertainty propagation method to power systems. Here, let's consider a single machine infinite bus systems where the uncertainty are encoded in the initial condition of rotor angle of a generator. We then apply our uncertainty propagation algorithm to estimate the moment up to second order of the whole system over 10 seconds. As we can see from this graph, the estimated moment can accurately match the true moment up to order 2, and we can see that the initial uncertainty in rotor angle is first being propagated into the velocity, and then this oscillation settles down, which means the system finally converge. So a brief summary of what I have introduced is we have seen how to form a sparse estimate of the kernel Kuban operator in both discrete time and continuous time Markov process. I then applied the learning algorithm to analyze global stability, analysis of unknown nonlinear dynamical systems, and also applied to propagating uncertainty in initial condition. I will next talking about interesting learning problems. That is the sparse identification of nonlinear system in decentralized setting. In some scenarios, the data are scattered across the network, and we need a multi-agent interacting with each other to collectively identify a common dynamical systems. And multiple multi-agent systems are ubiquitous. For example, people in the defense industry using swarms of robots to gather situational awareness of the environment, and the robot swarms are being used to carry out rescue tasks. When it comes to the multi-agent systems, the question is what protocol should be used. On the one hand, we have a centralized protocol where the computation is being performed centrally, and then being broadcast into the multi-agent systems. And then on the other hand, we also have a decentralized protocol where each agent communicate with their neighbor to form a decentralized estimate. Here we consider a decentralized scenario where each agent only interacting with their neighbor to learn the kernel Kuban operator or the adjoint of kernel Kuban operator, which encode the system dynamics collaboratively. So let's suppose each agent only have access to a local data. In reality, such a learning process is complicated by constraints such as communication constraint, which prevent agents to send their full estimate to their neighbors. So instead, each agent can only share a sparse estimate to their neighbor to form a sparse estimate of the operator U, which is the joint of the kernel Kuban operator. While sparse learning over RKHS is well studied, the sparse version is much challenging to handle, as the compression error can accumulate over time. So it's a basic consensus style update could cause a network average shift. And in order to demonstrate the problems of network average shift, I will first consider a simple example of a two-node network where each agent only trying to estimate a real value instead of estimate an operator. So now let's suppose we have a network that consists of only two agents, where agent A start with an estimate that is the real value of 1.0, and the agent B start with an estimate of 2.8. We can see that the network average at time 0 is 2. Now, because of the constraint of communication link, instead of sending this full estimate to their neighbor, we ask each agent to use a floor function to quantize their estimate to the integer. So in this case, the sparse estimate of agent A is 1 instead of 1.2, and the sparse estimate of agent B is 2 instead of 2.8. Now, after one round of estimate share, we can see that the network average become 1.5, which is different from 2. So this is the problem of network average shift if we only use a sparse estimate. To circumvent this issue, we ask agent to store the error due to compression. That is, each agent share the sparse estimate with their neighbor, but they should store an error due to compression locally. So in this case, we ask agent A to store an error due to compression, that is the difference between their true estimate 1.2 and their sparse estimate 1. And agent B carry out a similar procedure. We can see that in this case, the network average is preserved. So in short, we applied a similar mechanism to the operator learning in RKHS. That is, we ask each agent to share their sparse estimate of the covariance estimate, but they also need to store an error due to compression locally. And our paper have shown that under this modified sparse estimate, the network are able to preserve the initial average, and the decentralized learning algorithm is stable in the Lyapunov sense. We have applied our decentralized sparse learning algorithm to value iteration, and we have a simple example of an inverted pendulum where we can see that after 14 rounds of iteration, the value estimate will converge to a reference value of the pendulum swing up environment. In the last part of my talk, I will talk about the sparse online identification of nonlinear dynamics using the Koopman operator. So as we have previously seen, as long as we have an estimate of the kernel Koopman operator, we also have an estimate of its adjoint, that is which is also known as the conditional mean embedding operator. And these two operators encode stochastic kernel of a Markov process in the reproducing kernel Hilbert space. Our goal here is we want to perform a system identification on the fly with streaming samples, but also have control over model complexity. Here we leverage the well-established result, that is the conditional mean embedding operator, which is also the adjoint of Koopman operator, can be understood as the minimizer of an operator-valued least square regression. Using this regression formula, we then designed an algorithm to learn an empirical estimate of the operator U incrementally using operator-valued stochastic gradient descent algorithm. Again, in the online learning scenario, in order to scale the algorithm to larger samples, we need to have a control over the model complexity. But in the online learning scenario, we need to design the sparsification mechanism carefully such that the learning process is not derailed from its gradient descent. So in order to do this, we designed a new sparse learning mechanism that is shown in this graph. So suppose we have at type T0, we have an initial estimate of the operator U. We can then carry out an operator value stochastic gradient descent, which gives us an estimate of U1 tilde at time t equals 1. We then construct a sparse estimate of U tilde that is denoted by U1, but we impose a condition that is this sparse estimate should lies within an epsilon ball centers around the U1 tilde. We can then perform another stochastic gradient descent step to get U2 tilde and then compress it again such that the sparse estimate is also within the epsilon ball within this U2 tilde, and then we iterate such a process. By using this sparse online learning algorithm, we have established that the empirical estimate of the operator U are bounded in the mean square sense, and the arrow decay exponentially fast to a neighborhood of the true operator U lambda, and where the arrow will depend on the regularization parameter lambda and on the step size epsilon and also on the sparsification budget epsilon. So this is the result for the ID sample, and if we have a fast mixing Markov process, we can derive a similar bound, but instead of t, this will encode the mixing time of the underlying Markov process. Notice here we only give bound to the regularized version of the operator U, but we have more result in our paper where we try to bound the distance of the current iterate to the true conditional mean embedding operator in a suitable norm. And we also consider the hard learning scenario where this operator U might not be bounded, or it might not be a Hilbert-Schmidt operator on the RKHS, but we relax it to the operator U could be bounded on an interpolation space, could be a Hilbert-Schmidt operator that acts from an interpolation space between the RKHS to a true RKHS. So in summary, I have presented a nonparametric system identification with controlled growth in model complexity and finite sample performance in both centralized and decentralized setting. And this concludes my talks. I'm happy to take any questions.
Yeah, thank you very much. Thank you. Any questions?
Yeah, maybe I just can circle back to the comment that I wanted to make earlier, which is not a question, but maybe just something to think about, is that yeah, there are some papers and some theoretical results that explain what is seen in practice. Here, I understand that you don't have a neural network and parameters to learn, but at least in neural networks, when you have large neural networks compared to the amount of data you have, then and then you are applying gradient descent, so that's your minimization technique. You do converge to a solution that is sparse, and that's why I asked the question about the AIs. Were those the terms that you are learning? But it's not. But I just was wondering, like, can you learn a certain combination using neural networks and then somehow you converge towards sparsity without forcing sparsity or using a dictionary. I don't know. I have no idea, but just suggestion.
Yeah, thank you. Yeah, this is interesting. I never thought the neural network part. Yeah.
All right, thanks. Any other questions or comments?
My comment of this question is that the sparsity learning, usually people are associated with dictionary learning, right? And I guess you also use the term dictionary. But
Yes.
seems like the more established technique for dictionary learning, the starting point is like OMP, right? Orthogonal matching pursuit.
Yes, yes.
So, and obviously you knew about that, but you choose not to use it. So there must be a reason, right? Yeah.
In the first part, yeah, and so the first part when I use batch learning, my techniques, so it's very simple. It's actually due to computation issues. So this condition, it only involves this kernel function, the evaluation of kernel function at 2 points. So in order to carry out this coherent condition, I first start with a gram matrix using all the data points, and this gram matrix is very easy to construct. Then, in order to construct this sparse dictionary, I just delete every column and row that violate this condition. So it's actually very, very easy and very fast to implement. The orthogonal matching pursuit, if I understood it correctly, is a grading method. So it asks you to each time you select the dictionary that it requires more computation. And actually in the last part, when I'm using a sparse online learning, when I'm designing the online learning algorithm, and I said I required this U to stay within the epsilon bound of this non-sparse estimate. This part I used a variant of the orthogonal matching pursuit. So in the online learning scenario, I need to take care of the error of specification. I need to spend more effort on how to take care of the sparsification, such that this process so the sparsification does not derail the process too much. And in this part, I will need a greedy mechanism to enforce that the error stay within epsilon bound in order to perform the stochastic gradient descent and in order for it to converge. But for the batch learning scenario, one can also apply the sparsification based on orthogonal matching pursuit, but the one I'm using, I think, is much faster to compute.
Okay, thank you. Except the gram matrix is like a Hessian, right? You have to it's
no, it's a square matrix, but you only evaluate it once, then it's done.
Right. Oh, yeah. Okay. Just the size of it. Yes, but I understand.
Yeah.
I appreciate it. Yes. The size, if you have a lot of data point, your gram matrix can be fairly large, right? Isn't it?
Yes.
Yeah. Okay. Yeah. Thank you.
All right. Thanks. Other questions or comments? Yeah, okay. Yeah, I think we can just maybe ask you the same question I asked you like before, like which is like if you come back to your inequalities that we had, I think we already discussed it, right? With the inequalities that you had, like your approximation errors. Yeah, this ones. Yeah, if you remember, we had this discussion about learning the kappas and the phis by minimizing the right-hand side of this inequality. Yeah, did you make any progress in the meanwhile or not yet?
No, not really.
Yeah, okay. Yeah, anyway, that's all right. I mean, we can discuss it in Toronto, yeah, in about a month, yeah.
Yeah, sure.
Yeah, all right, okay. Thank you very much. Thank you. And
Thank you.
yeah, I don't if there are no other comments, I mean, yeah, Thank you again, Boya, for the nice talk, and thanks everyone, and see you next week for all the talks. Yeah, thanks. Bye bye. Bye everyone.